So this will be the last one about entropy, and from next time we will continue with a different methods. So this is lecture 7. We'll see two more applications of entropy method. The first one is a recent nice idea, some recent developments by Tingwei Chao and Han-Shun Yu, giving an entropy-based proof of a low-pass version of Kruskal-Katona theorem. So this is the first thing we're gonna see today. So let's recall, we've seen a version of an asymptotic version of Kruskal-Katona. In that version, let's recall, in this triangle maximization problem, where we given m, which is the number of edges, and we are maximizing t, the number of triangles. The graph G. So if you flip it around, this is basically the same as saying we given number of triangles, and our goal is to minimize the number of edges that sit in these triangles. You just for example, take the contrapositive of these bounds. Okay. The bound we prove is asymptotically tight, meaning that given t, the number of triangles, and the bound we have is 1 minus theta or 1 times whatever optimal. So we have by Schur's lemma, we get an asymptotically optimal 1 minus theta or 1 times optimal bound. Today we're going to see a version of Kruskal-Katona, yet still weaker, but at a certain point of value, it's optimal. We can remove this little 1. So let's see this low-pass version of Kruskal-Katona. So first, one piece of notation for any real, if we have a real, if we have a real number, x is real, then we can define also binomial coefficient x, choose, let's say d, to be as we define for normal binomial coefficient. So it will be x times x minus 1 times dot 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 x minus d plus 1 over d factorial. Okay, and we define this for x greater than or equal to d plus 1. D minus 1. Okay. All right. So what's the low-pass version? Of Kruskal-Katona. So this version is phrased in this the other way that we have above. But more general, instead of given K3, the number of triangles, and we're trying to minimize K2, the number of edges sitting in these triangles, we're going to do for general KD, how many KD minus 1 sitting in this KD. All right. So, so we have a family of, we think of KDs, given number of KDs as, we think of them as D subsets of a ground set. So we have some ground set, finite, let's say. For any family of subsets, for any family of D sets, A, we will denote, remember this notation, this is the shadow. This means, in particular, we could use this for the D minus 1 sets that are contained in some D sets in A. So let this be the family of all D minus 1 sets. We can think of this as the, so here is D equal to 3, right? This is D equal to 3. These are the D minus 1 sets, K D minus 1 sitting in KD sets, contained in some members of A. Now we have the bound. We have if we have that the size of A equals to some T choose D or some positive real T, this is real number T, then the shadow, the number of D minus 1 sets containing some D sets in this collection is at least T D minus 1. So first, let me make a remark that this is optimal for infinitely many choice of T. So this is basically the same intuition as we had when we do this triangle maximization problem. When we, given the number of, we're phrasing this way, but it's the same here. When we're given a number of triangles, then to minimize the shadow or the edges containing these triangles, the best we can do is to pack these edges as compactly as possible. Or we make a huge clique out of, we try to pack all these triangles into cliques to minimize the edges. So here's the same. Imagine, remark, optimal whenever T is a natural number, right? So when T is a natural number, this, the optimal example is basically just you take all D subsets of a ground set of size T, and all the other elements you don't care about other elements. How should I draw? Maybe I shouldn't draw it like this, where A is, for example, T choose all D subset of T. Okay. Plus maybe isolated elements that are not sitting in any D sets. Uh, maybe I will not write this. Okay. Okay, so how do we prove this? The idea is we're going to use this resampling idea we've seen improving Mantel's theorem in the last lecture, improving this Moon and Moser's inequality. So let's first associate the cardinality of A with the entropy of a random variable. So that's the usual practice we are doing now. We're going to sample a D set uniformly random from this family A. Then the entropy of this random D sets will be log of the size of A by maximality axiom. So we sample a random A uniformly from our collection, a random D sets, a uniform random D sets from A. Then we're gonna pick a random ordering of the elements in A. Let x1, this is a D set. So let x1, x2 to xd be a uniform random ordering of elements in A. All right. Then what's the size of the universe of this random variable taking values from? Well, the size of A, the range of A is cardinality of this family A. But then we also randomly label ordered elements in A. So we should multiply by d factorial of all possible orderings. So the entropy of A, this random A, is log of d factorial times A. We have by maximality entropy of A, entropy of this x1 to xd equals to log of d factorial times A. Okay, so we have on the left-hand side this familiar product space h1 x1 to xd. We're gonna use chain rule. That's the first thing that should come into our mind. But let me first expand this guy. Let me first rewrite this. This equals to, we know A equals to T choose D. So let's use that information. This just writes to log, wait, let me do the calculation here. This equals to A choose D, T choose D. T choose D, the D factorial get canceled out. So we just get T times T minus 1 times T minus D plus 1, right? So we have log of this, right? Log of product is sum of the log. So using that, we have this equals to summation of k from 1 to d log t plus 1 minus k. Okay. So let's estimate this joint entropy x1 to xd by chain rule. Let's split out the last element xd. We have h of x1 dot 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 xd equals to, well, first we reveal the first d minus 1 element of this d clique or d set, or interchangeably use d set or d clique for elements in script A. Then after reviewing the first d minus 1 vertices of this clique, we're going to review the last one. This is the conditional entropy, xd, x1, dot, 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 to xd minus 1. Okay, this guy, we're not going to do much. We will just use maximality to bound it. So now our task is to give upper bound on this guy. So here, let me remark, this by maximality, it just at most, what is this? Well, this guy takes value in script A, in the shadow of A, right? x1 to x d minus 1 is a d minus 1 clique contained in some d clique of A. So we have this, the range is this guy times, we have this random ordering here. So we should times d factorial. All right. So this is taking value over all ordered, sorry, d minus 1 factorial, ordered d minus 1 tuple in the shadow of A. So by maximality, this is at most log d minus 1 factorial and let me think, is this times the size of the shadow. So this guy, we're not going to do much. We're going to bound, our goal is to bound this from above. We're going to bound this from above. Okay. So our claim is let's define this guy. Let this conditional entropy xd, x1 to xd minus 1 to be, let's say, log r. We define r so that this is true. Okay. We're going to prove that we want to show r is at most t minus d plus 1. This is our goal. If we can show this, we will have, let's see, if this is true, then we have sum of right. So we have sum of k from 1 to d. This is calculation, but let's do it together. T plus 1 minus k. We know that from the top of the screen, this equals to the joint entropy, x1 to xd. We can estimate it in this way, just by maximality. We also know that this is at most. When we write it as the chain rule, we have the first term by maximality, log of d minus 1 factorial times shadow of A plus the second term, which is log R. But we know R, by our claim here, is at most t minus d plus 1, t minus d plus 1. So we plug in here. What do we get? Then, well, t minus d plus 1 is the last term here. Okay, so the last term get canceled out. We have the sum of log t plus 1 minus k d minus 1, k from 1 to d minus 1, is at most this log of d minus 1 click. Ordered this guy. Getting rid of the log, the left-hand side, let's move the summation inside to a product. This equals to log of product t plus 1 minus k, k from 1 to t minus 1, right? So we have this guy is at most this guy. Moving d minus 1 to the other side, we get the desired inequality. The last step is simple calculation. We have this is at least t minus 1, t minus d plus 2 over d minus 1 factorial, which is precisely the t choose d minus 1 we want to prove. Okay, so we need to prove that we need to bound this entropy by this guy. So first, let's think of why this is reasonable thing to prove. Well, let's suppose it's a little bit silly to think it this way, but it helps to see where this number come from. Let's say our ground set, our family A of D sets, just lives in this set of T elements. Okay, then after revealing x1 to xd minus 1, because we choose the d clique, so x1, x2 to xd, they have to be distinct elements from the ground set. So after revealing d minus 1 of them, the possible choices of xd drops down to t minus d plus 1. So this is the range of choices we can choose for xd, conditioning after revealing this. So by maximality, well, the entropy of such random variable, which has range t minus d plus 1, is at most log of that, right? So to prove this, we're going to use, we will prove, we will prove this. So for this, the claim is for any k equals to 1, 2 to d minus 1, we have the conditional entropy xk given all the previous one. Oops, sorry. Is at least log of r plus d minus k. Okay. If k equals to d, here, first of all, this notation is just a shorthand to write h of xk given all the bits before xk, x1 to xk minus 1. if D equals to K equals to D, this is what we define. K equals to D, we have XD, given all the smaller ones, XD, given all the smaller ones, which is log R, right? K equal to D, this is log R. So we want to prove that all these XK conditional all the previous bits, they are slowly getting larger when K is decreasing. Okay, so why this claim would prove what we need? What we need to show is this. R is at most T minus D plus 1. Because, let's first derive that. From this claim, we will have, using chain rule, so let's show that claim implies R is at most, what is the value? T minus D plus 1. By chain rule, we have the joint entropy x1 to xd equals to the sum of k from 1 to d hxk x less than k. This is chain rule. We've used it many times. And by the claim above, this is at least sum k from 1 to d log r plus d minus k. But recall, we also proved that this joint entropy equals to this guy. So let's copy it. Okay. And that implies what we want. This implies we have the same index, then this inside must be less than that. Cancel out k, r is at most t plus 1 minus d. As desired. So let's prove this claim. Before proving this claim, okay. Let's just first prove it, and then we'll explain some of the meanings of the inequalities involved. So to prove this claim, it suffices to prove the following. We suffices to show for any k from 1 to d minus 1, we have 2 to the entropy of xk given x less than k is at least 2 to the entropy of xk plus 1 given entropy of xk plus 1 given on the previous ones plus 1 here. If this is true, then we get the right-hand side simply because by telescoping this inequality, you just write For example, d minus 1, if you plug in d minus 1, here you have xt minus 1, d minus 1, and here is precisely, by definition, this is r. So you have r plus 1, and taking the log, you have log r plus 1, which is precisely what we need to prove for d minus 1. For d minus 2, you do the telescoping. This is d minus 2. Sum of two consecutive ones. Telescoping, this will get cancelled out. You will get what you need. Okay. So we just need to prove this inequality. Any question? This to this is just calculation. I will skip it, all right? This is by taking telescoping sum. So how do we prove this inequality on the left-hand side? We're going to do this resampling trick we've seen in Mantel's theorem. So the resampling, let's fix k. And the resampling trick is we have, let me draw a picture. Imagine d equal to 3. And I will fix k to be d minus 1 to be 2 here. Now we have x1 to xd sampled from A. So this is x1, x2, x3, which is xd here. Okay. Uniformly at random, sample from ordered elements of A. In the resampling thing, we're gonna have a Bernoulli random variable to resample one of these elements of the clique. So first we sample, but there the random variable resample is 1/2 balanced binomial Bernoulli random variable. Here we're gonna do optimization. We just choose this resample Bernoulli, but with probability p taking value 1 and with probability 1 minus p taking value 0. So this is our random resampling indicator R. And then we're gonna, which is independent of x1 to xd. Now we're gonna define sample this random R taking value x k plus 1. We are proving this with k fix. If R is 1 and equals to xk if R equals to 0. Okay. So this R could take value in this case when d equal to 3, k is d minus 1. So k plus 1 is this guy. This is k plus 1. This is k. So it could take one of these two values. Okay, this is where R could go. With probability p taking this value, 1 minus p taking this value. Now the key point is that this resampled vertex R has the same conditional distribution as xk plus 1 and xk. conditioning all the previous vertices x1 to xk minus 1. Note that conditioning on x1 to xk minus 1, the distribution of xk, xk plus 1, and r are the same. Okay. Well, these two are the same. It's trivial. Condition on the previous ones, xk and xk plus 1, they have the same margin, the same distribution. And r is just a convex combination of these two. So r is also the same. Now we can write the conditional entropy. We this implies, so what we need to estimate is this thing here, xk, condition on the previous ones, hxk, condition on the previous ones, but conditioning on the previous ones, they have the same distribution, so let's replace it by the entropy, conditional entropy of this random convex combination of xk and xk plus 1, condition on previous ones. Now, if you condition if you condition more, the conditional entropy going to drop. If you know more beforehand, then the new information you obtain is less. This is dropping conditioning thing. So we have this is at least, we're going to condition on more, less than k plus 1. All right. So at this point, we didn't prove much yet. We just show that because these, you can write this as xk plus 1 here. They have the same distribution condition on less than k. So we just proved that what we need to prove here is at most these without the plus 1. Okay, so how are we going to stick into the plus 1? One second. So how are we going to stick? Just by dropping conditioning, we can prove. So here, we only get h of xk less than k is at least h of xk plus 1 less than k plus 1 by dropping conditioning. But our goal is to have this plus 1 here. This is the key thing. To do that, let's estimate, we're going to make use of this little r and capital R. Now let's estimate this joint entropy. Consider this entropy H, the entropy of this random vertex and little r, conditioning on the previous ones. Okay. Let's use chain rule to expand it in two different ways. In the first way, by chain rule, let's review the capital R first. this equals to h of r x less than k minus 1. Then we review this Bernoulli random variable little r conditioning on capital R, well, these ones, and capital R. All right. One important observation here is that this guy equals to 0. Why? Well, conditioning on, look here, we have our x1, this is xk, this is xk plus 1 in our picture, right? In our picture, we have x1, dot, dot, dot. Here's xk plus 1. Conditioning on all previous ones, this is the conditioning part, less than k plus 1. Now, if you know what is R, first of all, xk plus 1 cannot take values from the vertex that xk has occupied. So after revealing sk and after revealing R, we will know whether R equals to xk or not, because xk plus 1 cannot take the same value as xk. Okay, let me write it down. Conditioning, we can just say as xk plus 1 and xk must take value let's just say as the values of xk as xk plus 1 and xk must take a different value. After revealing x1 to xk and R, we know what R is, little r is. Because if we know, maybe this is a little bit fast, we know whether R equals to xk plus 1 or R equals to xk, which is equivalent of knowing what little r is. Because in the previous case, little r equal to 1, and in the latter case, little r equal to 0. Okay? In other words, little r, the value, this random variable, is determined by x1 to xk and r. We proved this before. If one random variable is determined by the others, then the conditional entropy equals to 0. Okay, so we can first write this in this way. Now let's use chain rule to break it up into in different ways. Let's first review the little r and then review capital R. Chain rule in a different way, we have h of r equals to we first review the little r, then we review capital R, and little r. remember, this little r is a Bernoulli random variable independent of all these xi's. It just takes value 1 with probability p, and takes value 0 with probability 1 minus p. It's only correlated with r, capital R. It has nothing to do with xi's. So this entropy just binary entropy, h of p. So this is the binary entropy function, h of p. Recall that this is the function that we defined to be the value of p Bernoulli random variable entropy. And what's the second one here? Let's expand it using the definition of conditional entropy. So this equals to plus this term. This equals to, well, given x1 to xk minus 1, let's keep this guy. If r equals to 1, which happens with probability little p, right? If r equals to 1, then capital R we know is xk plus 1. Plus, with probability 1 minus p, times, let's copy this. If r equal to 0, which happens with probability 1 minus p, then capital R we know is xk. So it equals to this one. All right. How do we further simplify it? Well, okay. So this is this way. Now recall, we have, in the first way of expanding using chain rule, we have this joint conditional entropy equals to this guy. So let's write this here. Capital R, x less than k plus 1. And then this conditional entropy R less than k minus 1, right? This itself is less than conditional entropy of xk given the previous ones. All right? In the first estimate, we get that this is, maybe I should just write it here. Yeah. Give me a second. Okay, here, first of all, this is at most. Now this guy is 0. This guy is this guy, which is less than equal to this one. So h of xk, h less than k. Now we have, this is at most h of xk, h less than k. Good. I think something can cancel out. Which ones? Here, this one. Now, R is independent of xi's. So here, it plays no role in the additional information of xk. So it can drop this R equal to 0 without changing the entropy. Okay? And if you look at this term, turns to look a little bit different. Wait. Also, we should drop this after revealing it. What I want to say is, P Give me a second. No wonder I get confused. So this whole thing is 0, actually. You see, xk is one of the thing in here. This is x1 to xk. It's already revealed, so you get no information here. Okay. So we have altogether the purple one up there, entropy of xk, condition on the previous one, is at least this little hp plus p times conditional entropy sk x less than k plus 1. It starts to look like the thing we want to prove. All right. What we want to prove is 2 of this, 2 to this guy is at least 2 of this guy plus 1. And we're going to do, basically now we're just going to expand this and optimize over little p. So we're going to write the rest is optimization, basically. I will skip this. Then you do optimization. This is optimized when p equals to okay, maybe let me write a few words how we do the optimization. Let S equals to 2 to the this entropy on the right, xk plus 1, x less than k plus 1, and then we're going to pick this little p to be s over s plus 1. That's how we're going to do the optimization. Then you plug in here, you will get the desired inequality. This is pure commutation. I will skip it. Okay. So a remark here is, as I mentioned, if you just do drop conditioning, we can only get this inequality without the plus 1. The intuition behind this, why we gain the plus 1, is that remark. So we can think of this inequality as follows. In fact, the same proof implies what? The same proof, if you examine the proof, the same proof at some point shows that we have 2 to the h of xk plus 1 conditioning on less than xk is at least 2 to the h xk plus 1, h less than k plus 1. Why? Because the whole time we're keeping this term, right? And this term, if you look here, xk, sk plus 1, and r have the same conditional distribution, conditioning on all previous ones. So we can write this as xk plus 1 in the whole time, and the rest is the same. So we will prove, we can prove, instead of xk, we can prove xk plus 1 here, but still conditioning on all less than k. And the intuitive explanation of this inequality is that if we reveal Here is revealing x1 to xk. Here is revealing x1 to xk minus 1. So if you reveal one less element, which is this xk on the left, then possible we have one more choice for xk plus 1 in the range. That's the explanation for plus 1. Okay. Explanation is that after revealing xk, we have one less choice for xk plus 1, because all these xi's must take different values, distinct values. Okay. Any question? Now is our last application of entropy methods. It's a fairly recent development in the previous 2 years on this union closed conjecture. So let me first explain what is some definition. A family of sets of subset of n is called union closed if this family is closed under taking union, basically. In other words, if it is closed under taking union. I.e., for every A, B, if you take any two sets in the family, then their union also is a set in the family. Okay. There's a conjecture popularized by Peter Frankel saying that for any union closed family, there exists the popular elements of the ground set, which lies in at least half of the sets in F. So, conjecture for any union closed family F, there exists the popular element. So this F lies in 2 to the on ground set N, then there exists a popular element I in N lying in at least half of set in F. If true, this would be optimal. Just consider F to be the whole power set remark. Optimal if true. Consider F to be 2 to the N. Then every element is containing half of the set in 2 to the N. Okay. Previously, no proof is known that there exists a popular element lying in a positive proportion of sets in F. Previously, the best is like 1 over log. Up until 2 years ago, there's an entropy-based proof starting from Gilmer. Then later this improvement. So here we're gonna present a proof by Chase and Lovat which is similar to some other people's proof, refining the Skillmer's approach, giving a bound of roughly 0.38. So there exists a popular element lying in slightly more than 1/3 of the setting F. So theorem for any union closed F exists I lying in at least three minus square root 5/2. Let me call this guy phi, okay, which is roughly 0.38 proportion of setting F. Okay, good. One remark here I want to make. This theorem is tight for an approximate version. 3 minus square root 5 is optimal. Although 1/2, give me a second. Sorry, I'm a little bit sick, running nose. So for the exact version, if F is union closed, if it's true, 1/2 would be optimal constant. Here, this constant 0.38 is slightly worse than 1/2, but for approximate version, one cannot go beyond 0.38. So what is the approximate version? We say that a family F is approximate union closed if you 99% of the union lies in F. If you want to be precise, you can define 1 minus epsilon union closed. What it means is that when you uniformly random sample two sets from F, then the probability that the union lies in F is at least 1 minus epsilon. So in this approximate version, I'm not going to say more, but let me just say that in this approximate version, 0.38 is optimal. Where the optimal family F looks like F1 union F2, where this approximate version means if you take two uniformly random from the family, then the probability that their union lies in family is 1 minus theta over 1. If it's union closed, this probability will be exactly 1. We require the union to be in there. But here we just say, okay, with high probability, it's in the family. In this case, this is the example where it's tight. If you take roughly sets of n choose phi n, roughly, let me put an approximation. Okay, that's the first family, F1. Second family, you choose n bigger than 1 minus phi, and you choose the upper parts. Then it's not hard to check that every element is containing roughly this many proportion of the sets in here, in the union of these two. This is F2. And furthermore, this is approximately So here, every I in N is in roughly phi proportion sets in F, and it's approximate the union close. This is because if you take two, think of it randomly, take two sets here. If you take two other sets, their union definitely lies in F because it's on the top here. The size is large. So the only thing you have to check is if you take two sets here, the union lies in F, which means it lies above in here, right? If you take two sets uniformly random, then their expected size is what? 2 phi minus phi squared times n, right? Take two sets uniformly random, each of size phi n, so it's 2 phi minus the common element, which is phi squared. This equals to 1 minus phi, okay? Which is the cut line here. So when you uniform random take two elements here, the union will have size in this green region. That's why it's approximately union closed. Okay, that's just a remark. So let's forget about approximate version. Let's just deal with the union closed family. We're going to prove this proportion of the sets in any of union closed family will contain certain elements, certain popular elements. Any questions about the statement? Okay. So recall the binary entropy function, which is x log 1 over x plus 1 minus x log 1 minus x. 1 over 1 minus x. This is the number that records the entropy of a Bernoulli random variable with probability x. There is a claim that we will not prove. It's an analytic claim inequality for this entropy little entropy function h. We're going to use it as a black box. For any xy, we have the entropy or function of xy, the product is at least, and we're going to let little phi to be 1 minus this capital phi we define above. Okay, it's 1 minus this guy, which is what? Square root 5 minus over 2 minus 1. 5. 1 minus this. Yes. It's probably this. Yes. Okay. So this is a little phi. Now, the entropy function of xy is at least 1 over 2 phi times x times entropy function of y plus y times entropy function of x. So this is the analytic inequality we will not prove and use it as a black box. Claim 1, let's say. Okay. So what we will prove is this claim 2. Which says that if we independently sample two uniform sets in 2 to the n, we think of them as 0, 1 vectors. Think of their indicate characteristic vectors. So independently sample two elements from the power set. Think of them as 0, 1 length n binary vector, and assume that no element is too popular. Assume for any I in n, it's not containing too many of this A or B. The probability that this is just another way of saying I is in A, right? If you randomly sample set A, this is the characteristic vector. AI equals 0, just saying the element I in the ground set does not lie in A. Sorry, I should say does not lie in A. Okay. Suppose this probability is at least P. Okay. Then we will have the entropy of the join of these two, union of these two sets is at least P over 2 phi times entropy of A plus entropy of B. I think right. Here, my notation is not, I don't mean A and B are uniformly distributed from 0, 1. I just mean you have two random AB from this notation. Wiggly notation is for uniform distribution. So independent, take 2 for any independent random AB taking values in 0, 1 to n. Assume this is true, then we have this, right? This is the claim. Before proving the claim, let's just show how this claim will finish the proof. Okay. Claim 2 implies the theorem. So let's define little p to be the minimum of I in n probability that AI equal to 0. So I is not in A when A is uniformly chosen from F. Okay. From our union closed family. So once again, this means I is not in A. Our goal is to lower bound this 1 minus P. Lower bound this guy. If we can lower bound this guy, what is this P? P basically in the probabilistic language is locates the most popular elements, right? This locates in particular 1 minus P is the proportion of sets containing the most popular element in F, containing the most popular element. Yeah. This is those not containing I. 1 minus P is those containing I. 1 minus P become maximum. Okay. So our goal is to lower bound 1 minus P. Now, from what we're gonna do is to apply the claim, we need to take two independent random AB, taking value in 0, 1. What's the obvious choice? We also need to somehow link to the cardinality of F, right? So the obvious choice is AB are uniform random samples from F. Okay. Sample independently A, B in F. What do we have? We have by the claim, well, first of all, by maximality, entropy of A and entropy of B, these have the same distribution. By maximality is log of F of their range. By the claim says, first of all, if you univalue random sample AB, we are here. And this P is precisely the minimum that I is not in A. So this is satisfied. For any I, the minimum I of this is P. So we have this hypothesis satisfied. We can use this lemma claim to get that the entropy of the union is at least this guy. So the claim 2 implies entropy of the union HA union B is at least P over 2 phi of HA plus HP. HA HB is this, right? 2 times log of F. So just P over phi log F. Okay. Good. But notice, what is this? Our family is union closed. So AB are from F means A union B is in F by union closeness. We have A union B is in F. So A union B is some random set induced by some other random sets, but it takes value in F by maximality again. Entropy of this union, which is some random set from F, I don't know how it's distributed, but the entropy of this is no more than log of its range, which is log F. Okay. So on one hand, we have this is at least this. On the other hand, we have this one is at most that. So we get P over phi log F is most log F, implying what we need. 1 minus P is at least 1 minus phi, which is our psi. This 0.38 thing. Okay. Any questions so far? We are left to show This is where we use union closeness. We are left to show this claim 2. So in claim 2, we have two independent random binary string of length n. We don't know their distribution. We just know that there's no popular element, right? For any element, the probability that AI equals to 0 is at least p. We want to give a lower bound on the entropy of their union of these two sets. Well, we can view this set. This is itself a set in N. We can look at its characteristic vector, look at its i's coordinate, whether 0 or 1, and use chain rule to expand it. So by chain rule, we have the entropy of A union B equals to sum I in N which notation I should use? I want to write AI union BI, but that's not defined. So I should write A union BI. Okay, that's the ith coordinate of this vector A union B. And A union B, I abuse the notation A union B with its characteristic vector, conditioned on all the previous coordinates. And previous coordinate, I again use this notation. Okay. All right. Now we're gonna use this dependence property again. We're gonna lower bound this by h of A union B I. Now we're gonna replace the conditioning by more information. Then the additional information we get is less. This conditional entropy drops. So the more information is, instead of knowing all the bits of the union A and B up to I, I give you all the bits of each individual A and B up to I. This inequality sometimes also called data processing inequality. Okay. This is also sometimes called data processing. Just some fancy name, but we've seen this before, right? If what's in the conditioning has more information than this guy, then the conditional entropy can only decrease. This is certainly more information because this is determined by these two. All right. Now we're gonna estimate the right-hand side. To estimate the right-hand side, let's first do some estimate this conditional entropy. Okay, so let's use some shorthand notation. Write Px to be the probability of AI equals, we cared about the ith bit, so the ith bit equal to 0, given that the previous bit is this vector x, right? And similarly, define Qy is the ith bit of b equal to 0, given that the previous bit is this vector y of length I minus 1. By definition, by this definition, what is the expectation of Px? What's the expectation of Px over all possible x? Over all possible x, definition of Px is nothing but the probability of AI equal to 0, right? This is the probability AI equal to 0. I just write this probability in terms of conditioning form, then it's this. Okay. And similarly, expectation of y, Qy is the probability that Bi equal to 0. Now let's look at what's this guy. Expectation of x, h of p of x. All right. What is this? Let's write it. This is expectation of x, h of p of x is that thing, right? The probability ai equal to 0, a less than I equals to x is this one. Remember, now, for fixed x, this is basically, this whole thing is a Bernoulli random variable, taking value, wait a second, what I'm saying. Right, so this is a binary entropy function of this number. This is a fixed number. And this fixed number is the probability that of this random variable taking value 0, conditioning on that. So the binary entropy of x by definition is the conditional entropy of AI given all the previous bits. This equals to, let me first write it down, conditional entropy of AI given AI less than I. Okay. If you expand this guy using our definition, you will get this. So let me expand one step for you. This equals to expectation. Remember, conditional entropy is expectation over all instances of the thing we condition on. H of AI conditioning on a less than I equals to x, right? Now, what is this guy? This guy is precisely this, by definition of a little h function. Okay. Similarly, we have the entropy of little y of h of qy is conditional entropy of bi, conditioning on all previous bits. This is the setup. I'm going over time. So the rest of the proof is short. Maybe we will pick up from next time. Okay, that concludes today's lecture. We're going to finish this proof of the claim 2, which will finish this version of union closed conjecture, the weaker version. Any questions so far? Okay. If there's no question, next time where we're going to pick up is we know this claim 2 implies the result we want. All right. Just using the claim, we will get the lower bound on the entropy of the union of two uniform random sample sets from F. But by union closeness of the family, this union of these two random sets again is a random set from F. By maximality, it has entropy at most log of the range, which is the size of F, which then give us a lower bound on the proportion of sets containing the most popular elements. And to prove this claim, 2, we use chain rule to expand the union. And then we use this relaxation to lower bound it by knowing AI and BI previous bits individually. So this is some preparation. We're going to finish it next time. See you guys on Thursday.